Module 3, Lecture A, Reusable Functions. By the end of this lecture, you will be able to define functions that perform reusable chemical engineering calculations, choose clear parameters and return values for engineering functions, and document and test functions using representative calculation cases. Function basics. Function definition. In chemical engineering, a function is a reusable way to perform a specific calculation. Instead of repeating steps for tasks like pressure drop, heat duty, or gas flow estimates, engineers define the calculation once and apply it under different conditions. This makes their work more efficient, consistent, and easier to review. When defining a function, first identify the exact calculation it should perform. A good function has one clear purpose, such as finding a Reynolds number or converting gauge pressure to absolute pressure. Keeping functions focused makes them easier to test, reuse, understand, and maintain, while reducing errors when shared across engineering teams. Reusable engineering functions keep the calculation method separate from the specific input data. The same procedure can be reused for tasks like estimating pipe pressure drop or tank residence time, even when conditions change. This helps engineers build reliable calculation libraries, work faster, reduce repeated effort, and solve problems more consistently. Python code. Function definition. Functions make engineering calculations reusable by separating the general procedure from the details of a specific case. Parameters provide those case-specific inputs, and return values give back the calculated engineering results. The residence time minutes function calculates how long a fluid remains in a tank. It takes the tank volume and the flow rate as inputs, then finds the residence time by dividing volume by flow. The function returns this value in minutes, so it can be used elsewhere in the program. This function converts gauge pressure to absolute pressure. It takes the gauge pressure and atmospheric pressure as inputs, adds them together, and returns the resulting absolute pressure. The setup defines three input values for later calculations: a tank volume of 12 cubic meters, a feed flow rate of 3 cubic meters per minute, and a gauge pressure of 35 pounds per square inch. Keeping these values as inputs makes the code easy to adapt by changing them for different scenarios. The residence time function uses tank volume and feed flow rate to estimate how long fluid remains in the tank, helping assess process efficiency. The pressure conversion function then uses line pressure and atmospheric pressure to convert gauge pressure into absolute pressure for accurate engineering calculations. The code displays the calculated residence time in minutes and the absolute pressure in PSIA, making the results clear and complete. It also emphasizes that the same defined function can be reused with different inputs, showing its flexibility for other scenarios. The residence time function is reused with a volume of 8 cubic meters and a flow rate of 2 cubic meters per minute. The calculated result is stored and then printed in minutes, showing how the same function can efficiently handle different inputs for the same type of calculation. The script defines two reusable engineering calculation functions. One finds residence time by dividing volume by flow rate, and the other converts gauge pressure to absolute pressure by adding atmospheric pressure. In the example, a 12 cubic meter tank with a flow rate of 3 cubic meters per minute gives a residence time of 4 minutes, and a gauge pressure of 35 psi becomes 49.7 psi absolute. The residence time calculation is then repeated with different inputs, showing that the same function can be reused for similar cases. Pressure parameters. In chemical engineering functions, pressure inputs must be clearly defined because pressure can mean different things in different contexts. A reusable calculation should state whether it uses system pressure, reactor pressure, pump inlet pressure, or another specific value. For example, gas density depends on the relevant system pressure, while control valve flow must distinguish between upstream and downstream pressures. Clear pressure definitions reduce ambiguity and help ensure correct, reliable use. Pressure values must clearly distinguish between gauge pressure, measured relative to local atmosphere, and absolute pressure, measured relative to vacuum. Absolute pressure is often required for gas behavior and phase equilibrium calculations, while gauge pressure may be acceptable in areas like hydraulics if used consistently. Functions and documentation should state the pressure basis clearly, because confusing the two can cause serious errors in real plant systems, especially near atmospheric or vacuum conditions. Pressure parameters must clearly define their units, such as pascals, bar, atmospheres, or pounds per square inch, because the same number can mean very different things in different systems. A function should use one unit system consistently or explain how conversions are handled. Clear parameter names that show both the role and expected units make engineering calculations safer, more reliable, and easier to reuse. Python code, pressure parameters. Function names should make the type of pressure clear, since absolute pressure can differ from gauge readings. Including unit conversion also helps make pressure calculations safer and more reusable. Set atmospheric pressure to 101.325 kilopascals, the standard sea level value. This constant is used to convert gauge pressure to absolute pressure accurately and consistently throughout the calculations. This pressure conversion function changes gauge pressure into absolute pressure using atmospheric pressure with a standard default value. It first checks that the gauge pressure is not lower than negative atmospheric pressure, because that would imply a pressure below vacuum. If the value is physically impossible, the function raises an error instead of continuing. Absolute pressure is found by adding gauge pressure to atmospheric pressure. This matters because gauge pressure is measured relative to the atmosphere, while absolute pressure represents the total pressure exerted by the gas, which is needed for accurate scientific and engineering calculations. This ideal gas density function uses absolute pressure, temperature, and molar mass to estimate gas density. Before calculating, it checks that pressure and temperature are both positive. If either value is 0 or negative, it raises an error, helping ensure the result is physically meaningful. The gas constant is introduced as the value used in the ideal gas law to connect pressure, volume, and temperature. Before applying the law, absolute pressure is converted from kilopascals to pascals by multiplying by 1,000, since pascals are the standard pressure unit for these calculations. The code calculates ideal gas density using the ideal gas law rearranged for density. It combines pressure, molar mass, the gas constant, and temperature in Kelvin, then returns the resulting density value. To find the density of nitrogen gas in the reactor, use a molar mass of about 0.028 kilograms per mole, a gauge pressure of 200 kilopascals, and a temperature of 300 Kelvin. The gauge pressure must be converted to absolute pressure before applying the ideal gas law. To calculate nitrogen density correctly, first convert gauge pressure to absolute pressure by adding atmospheric pressure. Then use the ideal gas density function with absolute pressure, temperature, and molar mass. Repeating the calculation with gauge pressure shows why absolute pressure is needed for accurate results. The output compares reactor pressure values and their effect on nitrogen density. It reports both gauge pressure and absolute pressure, then shows the correct density based on absolute pressure alongside the incorrect result from using gauge pressure directly. The key point is that pressure must be clearly defined, because confusing gauge and absolute pressure can create hidden calculation errors. This script shows why gas density calculations must use absolute pressure, not gauge pressure. It converts a nitrogen gauge pressure to absolute pressure, then uses the ideal gas law with temperature and molar mass to find the correct density. It also compares this with the incorrect result from using gauge pressure directly, demonstrating how clear pressure definitions help prevent scientific calculation errors. Return values. In engineering, a function's return value is the useful result of its calculation, such as a pressure drop or flow rate. Returning the value keeps the calculation separate from reports or displays, making the function easier to reuse. For example, a pressure drop function should return the pressure drop itself so it can support comparisons, energy balances, and other engineering calculations. In chemical engineering functions, return values should be clear, predictable, and suited to the calculation. Each result should have an unambiguous physical meaning in units, such as a pressure or time value in a specified form. When a calculation produces more than one important result, the function should return them in a structured way so the output is easy to interpret and avoids repeated work. Clear return values make functions easier to test, validate, and reuse in engineering work. When a function produces reliable numbers or organized data, its results can be checked against known cases or simulations across different conditions. This reduces ambiguity, helps reveal errors, and supports dependable use in tasks like equipment sizing and process monitoring. Python code. Return values. Return values make engineering functions more useful and reusable. A function should perform a calculation and return its result, so the result can be tested and used in other parts of a program. This function uses the Darcy-Weisbach equation to estimate pressure drop in a pipe. It takes the pipe length and diameter, fluid velocity and density, and the friction factor, then combines them to calculate the pressure drop in pascals. The result reflects how pipe geometry, fluid motion, density, and friction contribute to energy loss along the pipe. The heat duty metric function calculates the rate of heat energy transfer. It uses mass flow, heat capacity, and temperature change, multiplying them to produce the heat duty in watts. The function then returns this value so it can be used elsewhere in the program. The pipe summary function returns pressure drop in 2 units. It first uses the pressure drop metric function to calculate the value in pascals from inputs such as pipe length, diameter, velocity, density, and friction factor. It then converts that result to kilopascals by dividing by 1,000 and returns both values for convenient use. The workflow computes key pipe flow results in metric units. It first uses the pressure drop metric function to calculate pressure loss in pascals from pipe properties and flow conditions using the Darcy-Weisbach approach. It then uses the heat duty metric function to find heat duty from mass flow, heat capacity, and temperature change. Finally, the pipe summary function returns the pressure drop, both in pascals and converted to kilopascals for easier reading. The validation checks confirm that the pressure drop calculation is accurate by comparing it with the expected value within a small tolerance. They also confirm that the heat duty is positive, showing the heat calculation is physically consistent. Together, these tests help verify that the functions are working correctly. The output summarizes the key calculation results by showing the pressure drop in pascals and kilopascals and the heat duty in kilowatts, with rounding for readability. It also reports whether the pressure calculation test passed and whether the heat duty is positive. Together, these checks confirm that the displayed results are clear and the calculations are valid. This script uses reusable functions to calculate key engineering quantities, including pipe pressure drop and heat duty. It applies the Darcy-Weisbach method, converts pressure drop to kilopascals, and computes heat duty from mass flow, heat capacity, and temperature change. The printed results are checked against expected behavior, confirming that the functions return usable values and can be tested reliably. Engineering interfaces. Parameter clarity. Clear parameters are essential in engineering functions because they define what information the calculation needs and how it will be used. In fields like chemical engineering, precise names help prevent confusion when similar terms may mean different things. A pressure drop calculation, for example, should clearly ask for items such as pipe length and fluid density. Vague parameter names make a function harder to trust, even if the math is correct. When designing functions, choose parameters that reflect the real engineering problem, not just the calculation steps. Use clear terms that a knowledgeable user would expect, such as flow rate or heat capacity, and distinguish related quantities carefully to avoid confusion. This makes the function easier to read, check, adapt, and reuse across similar physical systems. Engineering function parameters should clearly state their assumptions, units, and valid ranges so users interpret inputs correctly. This includes specifying units for temperature, distinguishing absolute from gauge pressure, and clarifying whether flow is molar, mass, or volumetric. Such details affect sizing, safety, and error detection, so well-defined parameters make functions more reliable and easier to use in collaborative work. Python code. Parameter clarity. Clear parameter names help prevent mistakes in engineering calculations. Include units directly in parameter names and make sure return values clearly describe what they represent. The heat duty in kilowatts function calculates the rate of heat transfer using mass flow, heat capacity, inlet temperature, and outlet temperature. These inputs include clear units, which helps make the engineering calculation easier to understand and reduces the chance of mistakes. The temperature change is found by subtracting the inlet temperature from the outlet temperature. This sign difference, measured in Kelvin, is used to determine the heat duty. The function calculates heat duty in kilowatts by combining mass flow rate, heat capacity, and temperature change. The result represents the rate of energy transfer, giving a useful engineering measure of heating or cooling demand. This function calculates the average fluid velocity in a circular pipe using the flow rate and the pipe's inside diameter. It first ensures the diameter is positive, then finds the pipe's cross-sectional area and divides the flow rate by that area. The result is the velocity in meters per second. The code first checks that the pipe's inside diameter is greater than 0. If the value is 0 or negative, it raises an error because such a diameter is not physically valid. This validation prevents meaningless calculations from continuing with invalid input. The pipe's cross-sectional area is found from the circle area formula using the pipe's inside diameter. Multiply pi by the inside diameter squared, then divide by 4 to get the area in square meters. This value is used in fluid dynamics calculations for flow through the pipe. The function calculates the fluid's average velocity in a pipe by dividing the volumetric flow rate by the pipe's cross-sectional area. With flow rate in cubic meters per second and area in square meters, the result is velocity in meters per second. The calculations estimate heat transfer rates and pipe flow velocity. First, the heat duty function is used to find the energy transfer for heating water from 25 to 80 degrees Celsius, and for cooling a hydrocarbon stream from 120 to 45 degrees Celsius, with results in kilowatts. Then, the pipe velocity function uses the volumetric flow rate and inside diameter to calculate the average fluid velocity in meters per second. The results are printed in a clear, readable format, so learners can quickly check the key calculated values. The water heater and hydrocarbon cooler heat duties are shown in kilowatts, rounded to 1 decimal place, and the pipe velocity is shown in meters per second, rounded to 2 decimal places. The code shows why clear parameter names matter in programming. Descriptive names make the purpose and units of values such as flow rates and temperature easier to understand, which helps reduce confusion and prevent errors in engineering calculations. The script provides 2 engineering calculation tools. One estimates heat duty from mass flow, heat capacity, and temperature change, while the other estimates pipe velocity from volume flow and pipe diameter. In the examples, it calculates a water heater duty of 74.7 kilowatts, a hydrocarbon cooler duty of 131.2 kilowatts, and a pipe velocity of 1.53 meters per second. The main lesson is to use clear parameter names and consistent units, so mass flow, volume flow, temperature, and related values are not confused. Input-output clarity. Functions need clear inputs and outputs, so the meaning of data is unambiguous. This is especially important in chemical engineering, where similar values such as mass flow rate and molar flow rate represent different quantities. A good function states required units and bases, such as Celsius versus Kelvin or mass-based versus molar-based flow, and labels outputs with their physical meaning, such as an outlet temperature or heat duty. Without this clarity, correct calculations can still produce misleading or unsafe results. Design function inputs and outputs from the user's perspective. Inputs should use information engineers can readily access, with clear definitions, such as what type of flow rate is required. If a derived value is needed, calculate it inside the function from familiar data and document any assumptions. Outputs should support the decisions users need to make, such as equipment sizing, so results are clear to engineers, operators, and analysts. Clear function inputs and outputs make software easier to test, maintain, and share. When an interface is well-defined, teams can design reliable tests and know what results to expect. This also prevents mistakes, such as confused units or hidden dependencies, from spreading through engineering tools. Clear functions support verification, reuse, and better engineering decisions, while reducing the risk of costly errors. Python code. Input-output clarity. Clear interfaces help prevent mistakes with engineering units. Function names should make the physical meaning obvious, and return values should be easy to interpret immediately. The heat duty function calculates sensible heat duty in kilowatts using mass flow, heat capacity, and temperature change. It first checks that mass flow and heat capacity are not negative, since these physical quantities must be non-negative. It then multiplies the 3 inputs together and returns the resulting heat duty. The code validates the inputs by checking that mass flow rate and heat capacity are not negative. If either value is below 0, it raises an error explaining that both must be non-negative. This prevents invalid inputs from causing incorrect calculations. The function calculates heat duty by multiplying mass flow rate, heat capacity, and temperature change. The result gives the heat transferred in kilowatts, which the function returns for use elsewhere in the program. A function calculates the outlet temperature in degrees Celsius using the inlet temperature, heat duty, mass flow rate, and heat capacity. It checks that the mass flow rate and heat capacity are positive to prevent invalid calculations. The result is a clear outlet temperature value for use in engineering applications. First, the function checks that the mass flow rate and heat capacity are both positive. If either value is 0 or negative, it raises a value error to signal invalid input. This prevents the calculation from continuing with data that is not physically meaningful. To find the fluid's outlet temperature, first calculate the temperature increase by dividing the heat duty by the mass flow rate times the heat capacity. Then add that increase to the inlet temperature. The result is the final temperature after the fluid absorbs the specified heat. The heat duty kilowatts function calculates sensible heat duty from mass flow, heat capacity, and temperature change. It first checks that mass flow and heat capacity are not negative, since negative values would be physically invalid. It then multiplies the three inputs and returns the heat duty in kilowatts. The calculation begins by setting three clear inputs for the water: a mass flow rate of 2.5 kilograms per second, a specific heat capacity of 4.18 kilojoules per kilogram per Kelvin, and a temperature increase of 12 Kelvin. These values describe how much water flows, how much energy it takes to heat it, and how much its temperature rises. Naming these inputs clearly helps keep later heat calculations accurate and easy to follow. The heat duty is calculated in kilowatts by multiplying the water mass flow rate, heat capacity, and temperature change. This gives the system's rate of energy transfer, and the result is stored as the heat duty value. The feed enters the system at 25 degrees Celsius. The outlet temperature is then found using the outlet temperature function, which uses the inlet temperature, heat duty, mass flow rate, and heat capacity to calculate the temperature change and add it to the inlet value. The output presents key results for a heat exchanger water stream in a clear engineering format. It reports the mass flow rate and heat capacity to 2 decimal places, then shows the calculated heat duty and outlet temperature to 1 decimal place. Together, these printed values summarize the water flow, energy transfer, and exit temperature in an easy-to-interpret way. This script estimates heat exchanger performance for a water stream by calculating heat duty and outlet temperature. It uses one function to find heat duty from mass flow rate, heat capacity, and temperature change, while checking for non-negative inputs. A second function uses the heat duty to determine the temperature rise and adds it to the inlet temperature. The script then prints the key inputs and results in a concise engineering summary. Meaningful return values. Engineering functions should return results that directly answer the design question, not just intermediate calculations. For example, a heat exchanger sizing function should provide useful outputs such as cooling water flow rate or heat load when needed. Avoid returning unrelated internal values because that makes the function harder to reuse and forces others to inspect its logic. The goal is to produce clear outputs that can support future engineering workflows. Function return values should be clear and meaningful, especially in engineering where units and conditions affect interpretation. A correct number is not enough if the user cannot tell what it represents or how to use it. Well-designed functions should return the key results needed for later calculations, such as vapor fraction and liquid composition in vapor-liquid equilibrium, so the output has real engineering significance rather than being just raw data. When designing functions, choose return values that fit the user's needs without exposing unnecessary internal steps. Too much output makes a function harder to use, while too little may limit practical engineering work. A pressure drop function might return only the pressure loss for design, but include flow regime information for troubleshooting. The goal is to provide meaningful results that match the context and help future users trust the function without inspecting its internals. Python code. Meaningful return values. Meaningful return values make engineering calculations reusable and easier to interpret. Using return dictionaries helps label units clearly, while tests check the approach against representative heat exchanger cases. The function takes heat, inlet temperature, and outlet temperature as inputs, then checks that the outlet temperature is higher than the inlet temperature. This ensures the temperature rise is positive before any calculation is done. If the outlet temperature is not higher, the function raises an error to prevent invalid results such as division by zero or negative values. To find the required cooling water flow rate, use water's specific heat capacity, 4.184 kilojoules per kilogram per degree Celsius, and the temperature rise from inlet to outlet. The flow rate in kilograms per second is found by dividing the heat load in kilowatts by the product of the specific heat capacity and the temperature difference. This gives the amount of water needed to absorb the required heat while reaching the desired temperature change. The code returns the engineering calculation results in a dictionary with clear labels for the heat load, cooling water flow rate, and temperature rise. This makes it easy to pass multiple related values from the function and use them in later calculations. The function returns a result dictionary that clearly labels the main engineering outputs: heat load, required cooling water flow, and temperature rise. This structured format makes the results easy to understand and reuse in other contexts. A representative design case is evaluated using the cooling water requirement function. It uses the heat load and the cooling water inlet and outlet temperatures. Here, 850 kilowatts, 25 degrees Celsius, and 35 degrees Celsius. The result gives the required water flow rate, heat load, and temperature rise with clear units, making the values easy to interpret and reuse in later engineering calculations. This example tests a cooling water requirement function for a smaller troubleshooting case. Using a heat load of 120 kilowatts and water warming from 20 to 28 degrees Celsius, the function calculates the required flow rate and returns labeled results for interpreting the system conditions. The tests check that the function gives reasonable engineering results. They confirm that the higher heat load requires a greater cooling water flow rate, and that the first case produces a temperature rise of exactly 10 degrees Celsius. Together, these checks help validate the function's accuracy and reliability. The output begins with a brief message explaining that the reusable function is returning meaningful results. It then reports the first case's design heat load, required cooling water flow, and temperature rise using appropriate numeric formatting so the thermal performance can be checked quickly. Finally, it shows the cooling water flow for a second troubleshooting case, giving a smaller scale comparison for validation. This script estimates the cooling water flow needed for a heat exchanger from the heat load and water inlet and outlet temperatures. It validates that the outlet temperature is higher, then uses water heat capacity to calculate the required flow and temperature rise. It compares a higher load design case with a lower load troubleshooting case, confirming that the design case needs more cooling water and that the temperature rise is as expected. The printed results give the key engineering values for both cases. Function testing. Representative test cases. Representative test cases should show that a function works in the situations it is likely to encounter, not just in one example. In chemical engineering, this means testing typical operating conditions, cases with known answers, and boundary conditions where mistakes are more likely. For example, a mixture density calculation should be checked with common mixtures, pure components, and edge compositions to confirm it behaves reliably. A representative test case should give enough context for another engineer to understand what is being tested and why the expected result is reasonable. Use physically meaningful inputs with the correct units and compare the output to an independent check, such as a hand calculation or trusted software. For engineering functions, realistic examples help catch coding errors and confirm that the calculation matches the intended assumptions, while unexplained unrealistic values provide much weaker evidence of real-world suitability. Representative test cases document how a function is expected to behave and help protect that behavior as engineering calculations change. By testing normal conditions, edge cases, and invalid inputs, they can reveal whether updates to correlations, units, or scenarios have introduced unintended errors. When a test fails after a revision, it signals the need to decide whether the changed result was intentional or a defect. This supports technical accuracy, accountability, and confidence in the function's outputs. Python code, representative test cases. Representative tests show how engineering calculations should behave by pairing inputs with expected results. When these tests pass, they build confidence that reusable functions are working correctly. The tank volume liters function calculates the capacity of a cylindrical tank from its diameter and height, both in meters. It first checks that both dimensions are positive and raises an error if they are not. It then finds the radius, calculates the cylinder's volume in cubic meters, converts that value to liters by multiplying by 1,000, and returns the result. This function calculates the volume of a cylindrical tank in liters. Before doing the calculation, it checks that both the diameter and height are positive. If either value is 0 or negative, it raises an error to prevent invalid or meaningless results. The calculation finds the tank's radius by taking half of its diameter, then uses the cylinder volume formula with the radius and height to get the volume in cubic meters. It then converts that result to liters by multiplying by 1,000, since 1 cubic meter equals 1,000 liters. A set of test cases is created to check the tank volume function. Each case includes a short description, the tank's diameter and height in meters, and the expected volume in liters. The examples use known cylinder dimensions, such as a typical lab tank and a simple geometry case, so the function's calculated results can be compared with expected values for accuracy. This test case checks the tank volume calculation for a small pilot vessel. It uses a tank diameter of 0.1 meters and a height of 0.5 meters, with an expected volume of 3.927 liters. The calculated result is compared with this expected value to verify accuracy. The process begins by setting a counter for successful tests to 0. It then goes through each test case and separates its key details, including the name, dimensions, and expected result, so each case can be checked individually. The test calculates the tank's volume from its diameter and height, then compares that result with the expected volume. It measures the absolute difference as the error, and passes the test if that error is less than 0.01. The test result is converted to a number, so passed tests add 1 to the running total, while failed tests add 0. The test is then labeled as pass if it succeeded or check if it did not. Finally, The program prints the test name, its status, and the calculated volume rounded to 2 decimal places. We test invalid input to confirm the tank volume function handles errors properly. Using a negative diameter should raise a value error because dimensions must be positive. A try except block checks this behavior, marking the test as pass if the error occurs and check if it does not. This helps verify that the function handles edge cases reliably. The code reports whether an invalid input test, using a negative diameter, was handled correctly. It then prints a brief summary showing how many numeric test cases passed out of the total, giving a quick overview of the test results. This script calculates the volume of a cylindrical tank in liters from its diameter and height in meters. It checks that both dimensions are positive, then uses the cylinder volume formula and converts the result to liters. Built-in tests compare the results with expected values within a small tolerance, report whether each test passes, and also confirm that invalid negative input raises an error. At the end, the script prints a summary of how many tests succeeded. Representative test cases. When testing chemical engineering functions, use realistic cases that match real process conditions, such as typical temperatures or flow rates. Check the results against trusted tools like spreadsheets or simulators to confirm they are not only error-free, but also physically reasonable. For example, a liquid mixture density calculation should be tested under normal operating conditions to see whether the output falls in an expected range. Good test cases should cover normal use, boundary conditions, and situations where expected behavior clearly changes. This helps confirm that a function works under typical inputs, near its limits, and in cases with obvious outcomes, such as higher density producing higher mass flow when volume flow stays constant. If results contradict basic expectations, such as heat duty decreasing when the temperature difference increases, the issue should be investigated right away. Representative testing uses concrete examples to show what a function is meant to do, including its expected inputs, outputs, and assumptions. In engineering, this helps guide design decisions, safety checks, and model validation, such as testing a vapor-liquid equilibrium function across relevant conditions. Good representative tests improve correctness, reduce silent errors, and make functions easier to maintain and apply responsibly. Python code. Representative test cases. Representative tests capture reusable engineering behavior by checking key calculation cases. Clear tests make even small functions safer and easier to trust. The heat duty kilowatt function calculates sensible heat duty from mass flow rate, specific heat capacity, and temperature change. Before doing the calculation, it checks that the flow rate and specific heat capacity are not negative, and raises an error if either value is invalid. This helps ensure the inputs make physical sense. The function first checks that the temperature change is not negative, and raises an error if the input is invalid. It then computes the sensible heat duty by multiplying the mass flow rate, specific heat capacity, and temperature change, and returns the result in kilowatts. A set of test cases is defined to check the heat duty function under different conditions. Each case includes a short description, the flow rate, specific heat capacity, temperature change, and the expected heat duty in kilowatts. The examples cover both normal heating situations and boundary cases, such as no temperature change, to confirm the function works correctly across a range of inputs. The test process starts with counters for passed and failed cases. Each test case provides the inputs for a heat duty calculation and an expected result. The calculated value is compared with the expected value using a small tolerance, and the appropriate counter is updated. This verifies that the heat duty calculation produces accurate results for known cases. To check the expected engineering behavior, compare heat duty at two flow rates while keeping specific heat capacity and temperature change the same. The calculation shows that doubling the flow rate from 1 to 2 kilograms per second increases the heat duty, confirming that higher flow requires more heat transfer. The heat duty test summary reports representative cases, including how many numerical tests passed and failed. It also checks expected engineering behavior by confirming that higher flow rate increases heat duty. A final boundary check verifies that when the temperature change is 0, the heat duty is 0 as well. The script calculates heat duty in kilowatts from mass flow rate, specific heat capacity, and temperature change, while rejecting negative inputs. It tests the calculation against expected results, counts past and failed cases, and checks key behavior such as higher flow producing higher heat duty. It also confirms that no temperature change gives 0 heat duty, supporting the function's reliability and expected engineering trends. Representative test cases. Chemical engineering functions should be tested with cases that reflect real operating conditions, not just a single example. Good tests include typical situations, extreme conditions, and cases where mistakes could easily be missed. For example, a liquid mixture density calculation should be checked with realistic mixtures, pure components, and boundary values to confirm both numerical accuracy and engineering relevance. To build confidence in a function, test it with cases whose expected results can be checked independently, such as hand calculations or trusted examples. Use simple cases to verify the basics and larger realistic cases to see how it performs at scale. The goal is not to test every possible input, but to choose representative cases and define acceptable agreement based on the context. Representative test cases help show whether reusable engineering functions handle both normal and problematic inputs correctly. Tests should define what inputs are acceptable, check important edge cases such as extreme temperatures or varied conversion values, and document why those cases were chosen. This record helps future users understand the reliability of the function and supports treating reusable calculations as trusted engineering tools. Python code, representative test cases. Representative tests help build confidence that functions behave correctly. Expected results should be checked independently, and edge cases should be included because they can expose hidden calculation errors. This function calculates sensible heat duty in kilowatts using mass flow rate, specific heat capacity, and temperature change. It first rejects physically impossible negative values for mass flow rate or specific heat capacity by raising an error. It then multiplies the 3 inputs and returns the resulting heat duty. The code validates that mass flow rate and heat capacity are not negative. If either input is below 0, it raises an error because these values must be physically meaningful for heat duty calculations. The calculation finds sensible heat duty in kilowatts by multiplying mass flow rate, specific heat capacity, and temperature change. Using consistent metric units keeps the result accurate and coherent. The test cases are organized as named scenarios for checking a heat duty calculation. Each case includes the mass flow rate, specific heat capacity, temperature change, and expected heat duty. Together, they cover normal heating examples as well as edge cases such as no temperature change and cooling, helping verify that the function works correctly across different conditions. The test process begins with a pass counter set to 0, then checks each test case in turn. For each case, It uses the given mass flow rate, specific heat capacity, and temperature change to calculate heat duty with the heat duty function. The result is compared with the expected value, allowing a tiny tolerance for floating point rounding. If the difference is small enough, the test is considered passed. This code checks whether a test case passed by comparing the calculated result with the expected value. If they are close enough, it increases the count of passed tests by 1, allowing the program to track how many tests met the expected outcome. The code checks each test case by comparing the calculated heat duty with the expected value. If the values are close enough, the test is marked as passing. Otherwise, it is marked as failing. It then prints a brief summary with the test name, rounded result, expected value, and status. The test checks whether the function properly rejects invalid input by using a negative mass flow, which is not physically possible. It expects the function to raise a value error and marks the test as passed if that happens. If no error occurs, the test fails, showing the function did not handle the bad input correctly. The test summary includes both the main test cases and one invalid input check. It updates the passed count if the invalid input test succeeds, reports whether that check passed or failed, and then prints the total number of passed tests out of all tests run. The script defines a heat duty calculation in kilowatts using mass flow, specific heat capacity, and temperature change while rejecting negative inputs. It then runs tests for normal heating, no temperature change, cooling with a negative duty, and invalid negative mass flow. Each result is checked against the expected outcome, and the script reports how many tests passed, confirming the function behaves correctly across these cases. In this lecture, you learned to define functions that perform reusable chemical engineering calculations, choose clear parameters and return values for engineering functions, and document and test functions using representative calculation cases. In the next lecture, Lecture B, we will go over numerical methods. Thank you for your attention. See you all in the next lecture.